A robust, decentralized physical infrastructure network requires a strict equilibrium between verifiable data storage and the economic incentives that sustain it. If demand on this system scales too quickly before that equilibrium is locked in, critical systemic imbalances threaten the survival of the entire network. Currently, specific architectural pain points are restricting growth, chief among them being errors in storage pricing algorithms and significant bloat in audit bandwidth. We cannot artificially drive network demand until the underlying infrastructure guarantees fair, accurate compensation for the node operators providing the physical hardware. Resolving these internal inefficiencies ensures that the network remains economically and technically stable as throughput increases. The upcoming release manifest introduces 3 primary architectural shifts designed to overhaul the protocol's core functionality. The first pillar of this overhaul is an economic correction of the storage pricing mechanism to protect those running the nodes. The second pillar is a cryptographic optimization of proof of storage audits to eliminate bandwidth bottlenecks. The third pillar hardens state machine replication and redundancy protocols to handle periods of high network churn. Collectively, these 3 updates shift the network from an experimental state into a highly optimized machine capable of processing real-world volume. Systematic clearing of technical debt allows the physical infrastructure to scale without degrading the economic or technical performance of the nodes. We begin at the data ingestion layer, examining the difference between how the system processes single-file uploads versus batched file uploads. In decentralized architecture, there is a common engineering assumption that merkle batching operations automatically yield systemic economic efficiency. However, a critical anomaly was discovered in the storage pricing algorithm regarding these large data batches. This split-screen model illustrates the discrepancy. On the left, we input a single data upload, calculating its baseline token compensation for the node operator. On the right, we process the exact same input byte size, structured as a merkle batch upload. Despite the physical data size being identical, the resulting token payment drops by 66% on the batch side. This occurs because a specific mathematical mechanism within the smart contract structurally underprices the physical space required for batched configurations. The immediate economic implication is that large batch uploads have been operating at a 3 times discount, at the expense of node runners providing the hardware. The upcoming architectural fix patches this smart contract logic, bringing batch pricing into parity with single upload pricing. Locking this fix is urgent. It must deploy before anticipated batch upload volumes increase and further penalize the network's physical providers. The final update is being compiled now, with exact timing and rollout confirmation following immediately after the code is locked. Correcting these misaligned pricing algorithms ensures that node operators are accurately compensated for the physical storage they provide, regardless of how that data is uploaded. Fixing specific pricing bugs points to a broader systemic need: transparent, accessible design documentation. To address this, architectural decision records, or ADRs, are becoming the new foundational standard for the protocol's development. This diagram shows the process. Publishing architectural logic alongside code establishes a permanent, queryable grounded truth. This is essential for the integration of upcoming autonomous agentic tools, ensuring agents operate using strict, verified parameters rather than assumptions. Making both the technical logic and the architectural reasoning public reduces reliance on one org-driven upgrades, increasing the decentralization of protocol governance. We now shift to the verification layer, specifically addressing network bandwidth efficiency during data audits. This is the legacy proof of storage model. To prove a node holds user data, it transmits an entire 4 megabyte chunk. As the number of nodes scales, moving these massive blocks places an extreme bandwidth strain on the system. The protocol upgrade addresses this directly through the tiny verified slice audit method. Using cryptographic extraction, the system generates a mathematically verified fractional slice from the original data block. This new proof relies on a minimal, highly lightweight footprint. This optimized approach has successfully completed its testnet validation phase. On the staging release train, this reduction in audit size has already yielded significantly faster data transfers in a test environment. While shrinking the audit size raises intuitive security questions, the underlying mathematics of the proof remain intact. This reduction in audit bandwidth mathematically preserves the exact same security guarantees as sending the full 4 megabytes. Optimizing cryptographic verification pathways is the primary mechanism that keeps a growing decentralized network from suffocating under its own audit traffic. Beyond auditing data, the network must ensure it survives physical hardware loss, leading us to the redundancy layer and state-machine replication logic. The network operates in a state of constant churn, a reality where physical nodes unpredictably enter and exit the decentralized topology. This simulation maps that churn. As active nodes drop offline, the remaining nodes must duplicate missing data to hit target replication factors. When they fall behind, red copy backlogs form. If these copy backlogs outpace the network's ability to recopy data, long-term permanence is at risk. The Replication Hardening update resolves this, allowing backlogs to clear rapidly as new links are established. Specific algorithmic fixes govern how the protocol prioritizes and duplicates missing state blocks. These recovery fixes allow surviving nodes to catch up instantly, effectively bridging the gap during heavy topological shifts. The overarching goal is maintained. The archive securely keeps multiple copies across different nodes, regardless of severe network volatility. Leaner audits free up the bandwidth required for these faster replication cycles to execute smoothly. Robust state replication serves as the final architectural safety net, guaranteeing data permanence even when the physical infrastructure is highly transient. Current upload volumes on the network are low, which means baseline node operator payments are temporarily suppressed. However, the newly balanced Merkle pricing equilibrium proactively ensures that as volume returns, node operators will be fully compensated for their space. At the same time, combining leaner cryptographic audits with replication hardening clears the most critical technical debt from the infrastructure. Ongoing group authority updates, known as X0X, are laying the secure groundwork for autonomous agent groups to interact directly with the storage layer. We are seeing immediate, practical deployment of this hardened architecture, with the P2P Foundation wiki already queued to begin uploading in stages. With a mathematically sound and architecturally hardened foundation in place, the protocol's engineering focus transitions from internal optimization to scaling market demand.